Blue skies and red sunsets, the journey of sunlight. Welcome to our journey through the colors of the sky and the mesmerizing hues of sunset and sunrise. Have you ever wondered why the sky is blue during the day and transforms into vivid yellows, oranges, and reds at sunset? Why the sky isn't any other color? Couldn't the sky just as easily be green or yellow? Let's start with the daytime sky. When the sun is high, its light travels through Earth's atmosphere, where it encounters air molecules, mainly oxygen and nitrogen, and tiny particles. Despite what our coloring books might suggest, the sun isn't yellow. Light from the sun appears white because it contains all colors of the visible spectrum, from red to violet. A simple way to demonstrate that the sun's light is indeed white is by holding up a white sheet of paper outdoors during the day. Each constituent color has a different wavelength. Red and orange light have longer wavelengths, while blue and violet light have shorter wavelengths. This interaction of light with the molecules and particles scatters the light in all directions, a phenomenon known as Rayleigh scattering. Picture a boat in the sea that scatters the small waves but lets the longer ones pass without problem. So, it turns out that the blues, violets, and greens tend to be scattered more easily than reds and oranges. Violet is scattered the most, followed by blue, then green. However, the sun doesn't emit much violet light, additionally a part of it is absorbed by the high atmosphere. Moreover, our eyes aren't very sensitive to violet. Green isn't scattered as well as blue, so the predominant color ends up being blue. The predominant scattering of the shorter wavelengths results in the blue color of the sunlit sky, since in directions other than toward the sun, we see mainly scattered blue light. As the sun moves lower in the sky, the path of the sunlight through the atmosphere becomes longer. As the path lengthens, there's more opportunity for the blues, violets, and greens to be scattered or reflected away from our line of sight. What remains are the oranges, yellows, and reds. So, as the sun gets lower and lower, its light passes through more atmosphere, rendering it yellower and redder. Additionally, dust, smog, and other particulate matter in the atmosphere absorb and scatter blue and green light more than orange and red light. This absorption further deepens the reds and oranges, making the setting sun and sometimes the whole western sky glow red. The same principles apply to sunrise. This is why sunsets and sunrises can look so different from one place to another and even from one day to the next. The amount of dust and particles in the atmosphere can vary, creating an endless variety of beautiful pictures. As the sun sets or rises and its blue light is filtered out, the remaining warm colors illuminate clouds, creating a spectacular display. The clouds receive the red and yellow light and appear red and yellow to us. Notice also how the sky is most vibrant overhead but fades to pale near the horizon. This is because the light from the horizon travels through more atmosphere, scattering and rescattering, in so many directions so many times that less blue light reaches us. The same principles apply to the moon. When the moon rises or sets, it can appear yellow, orange, or even red, depending on the atmosphere's conditions, just like the sun. It's just that there's not enough light from the moon to illuminate clouds, and so you don't see the cloud colors during moonrise and moonset the way you see them during sunrise and sunset. The endless variety of colors and patterns in our skies reminds us of the beauty and complexity of our atmosphere. So next time you gaze up at the sky or watch the sun dip below the horizon, you'll know a bit more about the science that creates these awe-inspiring views.